The last example in this chapter is Bayesian analysis. We're going to look at an example case of Zika virus causing birth defects. But first, brief introduction. We did Bayesian analysis in the introduction to probability way back at the beginning of the semester. So the Bayesian analysis is predicated upon the principle that we start out with some knowledge, but that's the current knowledge, which we call prior probability. And then we have some intervening event. Okay, when additional data is collected, then we look at how likely is this additional data for a given prior probability. And based on that, we come up with posterior probability for the event. So posterior probability is given by prior probability times the likelihood of that event given the intervening data. Okay, this may sound kind of confusing, but when you look at the example, hopefully it won't be that confusing. So the same thing can be written as, okay, posterior probability is the new knowledge. Okay, so you have prior knowledge and new knowledge. Prior knowledge is the prior probability, new knowledge is the posterior probability that's given by multiplying by likelihood. Okay, so that's the foundation. Now the example here is that we have a Zika study where 125 infected women, pregnant women, found to be 58 of them had adverse pregnancy outcome. Okay, so that's the initial study. Then there is a more recent study of 76 births, of which 42 of births by women infected with Zika virus, and then 42 were found to have severe related complications. Okay, so now how do we take that information and try to estimate the birth defects in a population of 100,000 based on this new study? Okay, so and the underlying assumption is, of course, both studies have the same environmental factors. So that would mean there were only two studies. First of all, if there are more studies, then we probably we would take all the other studies into consideration in figuring out the result that we are looking for. That is to estimate prevalence of Zika-related birth defects in this 100,000. But for our purposes, let's assume that there was only one previous study, which was that. And of course, the underlying true rate of Zika is the same in both cases and in the 100,000. So that's the study results are applicable to the 100,000. The first approach is simply to ignore all of that, and we only look at the most recent study, and we don't even do any simulation. We just simply use formulas to figure out what would be the proportion or what would be the prevalence of birth defects in this 100,000 population. Okay, so no simulation. So in that case, what happens is that our estimate, so remember, we are ignoring the earlier study, we were only looking at the second study. So 42 out of 76. So probability of adverse outcome is this ratio 0.5526, and then using binomial probability theory, so we can find standard error of this p estimate, which is given by this formula. Okay, so plug in the values and you get the standard error. Then we can develop a 95% confidence interval for the probability of birth defect. So that's given by this point estimate plus or minus a sampling error. The sampling error is given by our normal distribution z-score, which in this case, when you have a large population of binomial, it can be approximated with the normal distribution. So there are theoretical basis for this. So you get the z value for 95% confidence interval, which is 1.96, multiplied by the standard error. So this part is the sampling error, and then you go plus or minus p plus or minus that sampling error will give you the confidence interval. So we can say that out of that 100,000, if you multiply these two probabilities to 100,000, so you get a range of how many babies in the population will have Zika related adverse outcomes. And this is the formula from the first principles, and Excel has a function for computing that part, okay, that the sampling error part, where the function is this, where alpha refers to, so if you have 95% confidence interval, alpha is 0.05. So it's 1 minus that part is alpha, or 1 minus alpha is the 95%. And then standard deviation is that standard error. And the size is your sample size, and since we are looking at the proportion, the sample size will be 1, or we can enter 100,000 there, but we will use 1, and then we will develop the rest of the computation. So let's do this part first. Let's get head on to Excel. Okay, so we have the given values. Okay. These are the study results, right? And we want confidence interval for 95%. 95% confidence interval will be on the lower side you have 2.5%, on the higher side you have 97.5%. So the middle part is 95%. Okay. So we're going to ignore this. We're only looking at the new study. So the proportion is that divided by that. Okay. And then the standard error is square root of, right, p times 1 minus p divided by the sample size of 76. Okay. Well, and then we can do the same thing here. Well, we really don't need that for our analysis, but let's go ahead and, for the sake of similarity, so let's do that. Okay. So now standard error from the new polling result, okay, is that. Okay. Well, okay, so we can do a sampling error. Okay, and that would be that times 1.96, which is really, you need to really put that 1.96 outside, and then use like norm. So you want norm dot inv, right? And then norm s dot inv. So you'll get the z-score, norm s dot inv, and this difference is the probability. So we need to norm dot s dot inv of that, so you get 1.96, and then you would instead of hard coding 1.96, you would do that. Okay. So that's our sampling error, and we can get the sampling error using the confidence formula. So confidence dot norm, and the alpha value is 2 times that. So that's the tail. This 2.5 is the tail on the left side, and you have a similar 2.5 tail on the right side. So you do 2 times H2 and then the standard error and 1 for sample size. And that gives you the same thing. So, right? So you can do it either way. And then the confidence level for P will be, okay, so it's that minus the sampling error, and then that plus the sampling error. Okay. Now, of course, you're going to get the same answer if you use that, obviously. So that plus the sampling error. Okay, let's put the border back. Now, how many babies will end up with adverse effects? So that would be, so you take the 100,000 and make that absolute reference times the lower confidence level, right? And then, okay, so that would be the number of babies that will be affected in a population of 100,000. So in this approach, we are not doing any simulation. It's straight parametric method where we use formulas to come up with standard error and sampling error, and then we have our estimate. Obviously, there is not a whole lot of confidence in this because it is based on one single study of 76 exposed mothers.